Right, can you see the slides on the screen? Right, thank you, Najia. Right, so in the last class, we have learned about the concept of recombination. So we have learned that there are three types of recombination modes or recombination mechanisms. The first one is radiative recombination or band-to-band recombination. The second one is a Shockley Ritz-Hall or SRH recombination, and the third one is Auger recombination. And we have discussed examples of when do you have one or more types of recombinations in your semiconductor materials or devices. Okay, for example, if you are given a gallium arsenide with a perfect lattice, for example, and lowly doped or lightly doped, then the recombination mode will be radiative and just radiative, right? But on the other hand, if you are given the very same material, gallium arsenide, perfect lattice, but heavily doped, 10 to the 18, 10 to the 19, then you should also expect Auger recombination to be around on top of the radiative recombination, alongside radiative recombination. And the total recombination that you have in your materials will be the superposition result of your one or more recombination that you have. Okay. So we have also learned that when you talk about radiative recombination, so it is normally happening in a direct bandgap semiconductor, like gallium arsenide, gallium telluride, indium phosphide, gallium nitride, and others. And we don't have it in indirect bandgap semiconductors like silicon, germanium, right? Typically. And for SRH, if you have defects, imperfect lattice, dislocations, and other types of imperfections in the lattice, you are going to have SRH in the semiconductor material. And on the other hand, when you are working on heavily doped semiconductors, typically more than 10 to the 17, you should expect Auger recombination. Right, so let me just ask you this question, and we discuss a little bit before we move on to the next part or the final part in this topic. So if you are asked whether recombination is good or bad, what would your answer be? If you are asked whether recombination is good or bad, what would be your answer? Anyone? After what you've learned so far? Okay, Bala said recombination is good. All right. Any other answers? Is recombination in general good or bad? Anyone else? What do you think of answer? Fatul, what do you think? If you're asked whether recombination is good or bad, what would you say? Fatul? Yeah, in whatever perspective, doesn't matter. you can tell me your perspective. I'm asking a very general question. Okay, Patience said, I think it can be good and bad as well. Okay, Patience said both. It can be good, can be bad. Right, that's interesting. So, Fatul, what do you think? Then we discussed a little bit before we move on. Let's have 3 answers at least. So we heard good, we heard both. All right, so you said both as well. Okay, so let's hear from Bala perhaps. Bala, would you like to explain a little bit why do you say it's good? And you can unmute yourself.
Because recombination also is two of it is radiative, so you get light photon production, so you can use it for application like LEDs. And then one of it, I forgot which one was it. I think it was yoga. Yoga, I think that has the heat application that it produces heat when the recombination happens. There's heat, so you can also do heat harvesting. I think you mentioned, doctor. So for those benefits, I think it's good.
All right, okay. Thank you for your perspective. All right, let's hear from Pedron. You can unmute yourself as well, Pedron. You said both.
Yeah, both. Can you hear me?
Yeah, I can, but you can just talk. Let me just hear you.
I think for the good side is like what Bala say. For when recombination, you can use a LED and then you release the light emission.
Okay.
And for the bad side is for the semiconductor where we don't I think when we don't the impurities, right, when the recombination occurs, there will be no free electron. Yeah. So that the report is that the semiconductor buffer.
Okay, right, thank you. Okay, that's another perspective. Fatul, would you like to add to the points on both good and bad? You can unmute yourself. Okay, all right. You can just write down later on in the chat box. Okay. So yeah, it can be, well, generally it's good and bad, right? Depending on the specific use, if you like, right? So it's good in the sense that you need to have radiative recombination for optoelectronic application, just like what Bala and Pesron said. So just imagine if you are using direct semiconductor materials, but and you want to use the material for LED or laser, for example, but then your radiative recombination is very poor, then you will not be able to get as much light as possible because the radiative component is not performing well. So in that sense, you need to have a good level of radiative recombination. So you want recombination to happen for optoelectronic application when you emit light. When you say it's opto, then it's light related semiconductor applications. It can either be emitting light or absorbing light. Okay. For example, if you talk about emitting light, then of course you're talking about lasers, LEDs. You're talking about absorbing light. You're talking about light sensors, solar cells. They are all optoelectronic devices. Okay, any electronic, but related to opto means light and semiconductor devices. Either they are emitting or absorbing. So in that sense, you need recombination, radiative recombination to take place. On the other hand, it's bad because, as Pesun said, it will remove or it will trap the existing carriers in the device. So then you will end up with a lesser amount of carriers that you're supposed to have, for example. For example, if you can give an example, for example, solar cell, you are already absorbing the photon with the right energy, then photo generation already took place. Then you've got your electron hole free pairs available in the material, but then they cannot be collected due to recombination. So in that sense, it's bad, right? So So now, even though when you talk about generation and recombination, it looks like generation is positive, but recombination is on the other hand. But when you dive into recombination in details, then we can see that it's not bad in general, right? It can be good, it can be bad, depending on the applications. Okay, right. So that's what I want you to get from this concept of recombination in essence. Right. How do you then tell the quality of the material? So this is one one important parameters that you need to know when you are working with a semiconductor device. Let me just switch one. Oh, okay. So one way to tell whether you are working with material with a good quality is by looking at the lifetime, total lifetime. So lifetime here means the lifetime of your careers, right, in the material or in your devices. So total lifetime tau. Why is not writing up? I don't know why. Why it's not coming on my screen? You can still see my screen, right? Can you? Ah, okay, it's just my stylus and maybe battery good. I'm trying to write down, but nothing comes up from my stylus. It's all right. Kita pula, huh? So when you talk about, let me just point using cursor mouse. So lifetime tau. So it is a measure of the life of your careers. Macam jangka hayat lah. So lifetime measures the time your carrier survive since generation to recombination. Once you generated the carriers until they recombine, the duration they survive is called lifetime. Okay, jangka hayat lah, jangka hayat apa carrier tu . So generally you want the lifetime of your careers to be as long as possible, especially in the case when you have to extract the carriers to be out of your semiconductor material or device. Okay, kalau let's say jangka hayat dia short, maksudnya before you can extract the carriers to outside of the device in order to complete the circuit, for example, then they are already gone. When tak sempat nak keluar, they're already gone because of the short lifetime. Okay, this short or long lifetime tells you about the quality of the material that you were working on, the electronic quality to be exact, right? So typically, if you're working on a material with a high lifetime, for example, katalah I ada silicon wafer, then the lifetime of my silicon wafer is 300 microsecond. So the order is typically around microseconds, nanosecond. It depends, right? Microseconds, if you talk about silicon, is considered good. Hundreds of microseconds is considered good. On the other hand, the second material, same material, may have a lifetime of say 100 nanosecond. So of course, in this case, the one with microsecond lifetime is a lot better because that shows the carriers can survive longer by 3 orders of magnitude, right? From micro to nano, 3 orders of magnitude difference, right? So the total lifetime, when you talk about recombination, is given by 1 over tau. We show by using my cursor 1 over tau total. So which equals to 1 over tau due to radiative recombination plus 1 over tau due to Auger recombination and plus 1 over tau due to SRH recombination. Only if you have all the 3 at the same time. So for example, if you only have 1 or 2, then you will say if you are working on radiative recombination and Auger, so you just have to forget about SRH, right? So the process with the shortest carrier lifetime dominates. So whatever process, either radiative or OJ or SRH, with the shortest lifetime will dominate the total lifetime. Okay, so maksudnya kalau satu proses cause your carrier to survive longer, but you have another one causes your carriers to survive only short lifetime, then that short lifetime will dominate the whole lifetime calculation, and it will show up in your measurement. Okay. So note that for a semiconductor material with a given doping level, the carrier lifetime of the three recombination mechanism are only constant for the specific case of low injection condition, and this really depends on what you have in your semiconductor material. So when you are talking about the lifetime or the quality of the material, your carrier lifetime can be translated into the parameter that we call diffusion length. Okay, what is diffusion length? So diffusion length is average length of a carrier, average length a carrier move between generation and recombination. So remember, the measurement is between the point of generation until the point of recombination. So, and this is the lifetime between G to R, macam jangka hayat hidup kita lah, lahir sampai meninggal dunia. So then your age is here. So that's pretty much the same thing if you translate that into a career. So the distance travel within this lifetime from G to R is called diffusion length. So essentially it's the distance traveled by the carrier between generation and recombination. So macam lifetime lah, cuma the dimension is distance, but it exactly translates the same thing, right? So semiconductor materials, they are heavily doped, have greater recombination rates, and consequently having shorter diffusion length. For example, okay, if you're working on semiconductor materials, they are heavily doped. You're talking about, say, 10 to the 18, 10 to the 19, for example. Then we have discussed last time about the mobility. If you can still recall, mobility is inversely proportional to the doping level, right? Because if you get heavily doped, as if you're pushing many people into the same small room, and it's very hard to move around, right? Because it's too crowded. So that will affect the survival of the carrier in that sense. So if you're working on heavily doped semiconductor material, you should then expect shorter diffusion length, right? So that means this also translates into shorter carrier lifetime. So yeah, if you're comparing 10 to the 16 per centimeter cube punya doping level, and the other material is 10 to the 20, for example, then if you assume other parameters within these two materials are the same, then you should expect longer lifetime and longer diffusion length for 10 to the 16, and shorter lifetime, shorter diffusion length for 10 to the 20, right? Due to heavy doping effect, right? Due to heavy doping effect. So high diffusion length are indicative of materials with longer lifetime, and is therefore an important quality to consider with semiconductor materials. So this is one crucial parameter, if you like, if you're working on solar cells, if you're working on integrated circuits, you're working on some other semiconductor materials. And how does the diffusion length, how is the diffusion length related to the lifetime is given by this equation below, L equal to square root of d tau. And L is the diffusion length, distance traveled by the carrier from the point of generation till the point of recombination, and that's given by square root of d, diffusivity of the material, of the carrier in the material, times the lifetime. So maksudnya from here you can see straight away, it's very obvious that L is proportional to tau. Okay, macam tadi lah saya punya example tu. So your jangka hayat is actually the life that you have gone through, right? So jangka hayat carrier is actually the distance that the carrier has gone through before it recombines, right? So tau, and again you have to bear this in mind that tau is the tau total that we talked on the previous page. And that depends on whether you have radiative or OJ or SRH or a combination of one or two or more, right? So that will be brought into this tau here, which will eventually determine your L, right? For example, so you can have a look at these two graphs. So let's have a look at the one on the top, top left. So what you see here is donor density or doping level, if you like, on the x-axis, and the same thing is also true for the second graph, right? Acceptor. So this one is ND. You're talking about N-type. And the second graph on the right below is NA, P-type. And then we are looking at lifetime on the primary y-axis in seconds, and then we are looking at diffusion length on the other hand on the secondary y-axis, right? So you can see if you the lifetime is given by this black curve. Tengok kat sini arrow pointing to the left axis, the red curve is pointing to the right, so that means it's showing the diffusion length. So you can see here, you can see from here that when you increase the doping level from 10 to the 13 up to 10 to 20, you can see the diffusion length and the carrier lifetime barely changes if you talk about 10 to the 12, 10 to the 13, and starts to show some small effect at 10 to the 14, 15. But you can see when you go above 10 to 17, a huge gradient, right? A larger gradient can be spotted on the curve. So that shows, the black one shows the lifetime, the drop of lifetime when you increase your doping level beyond 10 to 17. And as a result, if you put this tau into this equation, L equals to square root d tau, you're going to get your diffusion length proportional to your lifetime. And the same thing can be seen from p-type material as well. Okay, so here we understand that when you increase the doping level, you should expect a lower lifetime, hence lower diffusion length. Okay, so later on, why is this important? So when you learn about your devices later on, okay, when we talk about PN junction, we're going to talk about the thickness of your P, the thickness of your N, the doping level in the P, the doping level in the N, and then what sort of resistance you're expecting, what sort of current you want. And this will be somehow determined by the thickness and the doping level of each layer that you have in your device. So, and you may have more than one PN junction. For example, you may have PN, 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 or you may have PIN and stuff. So, so you're going to see later on that to be able for you to create a device that is conductive, you need to go for heavy doping. Okay, kita dah belajar itu kan, the doping level, the conductivity is the inverse of resistivity, and for you to be creating a conductive layer or conductive device, you need to heavily dope the layer. But when you heavily dope the layer with the aim of getting a more conductive layer, you're also sacrificing your lifetime and diffusion length of the carrier at the same time. Okay, so that's why when you learn this concept, you're going to learn that you want it to be conductive in order to have small resistance in the device. But when you push it to be too conductive, you are going to compromise your carrier lifetime and diffusion length. So maksudnya, bila you dapat conductive layer, conductive device, that doesn't necessarily translate into a better device performance because you are compromising your lifetime and diffusion length at the same time. Maknanya conductive, but then the carriers generated perhaps light by voltage or whatever, you are generating the carriers already, but then they will not survive for a long distance or for a specific distance before you can extract because the lifetime is already compromised, the distance is already compromised, the diffusion length is already compromised in the name of getting a more conductive layer. So bila you kerja nanti, you're going to see that when you develop a new technology, a new layer, a new device, new material, whatever, so there's always a trade-off between being too conductive and compromising, or you want lifetime. So it's something you just have to decide. Okay, for example, you're going to learn later on that if you talk about solar cell as a PN junction, for example, The P layer is typically 10 to 16, and the N, the very thin layer, is very thin. It's the order of 200 nanometer, and the P is like close to 200 micron, and the N has to be heavily doped. And you will see that when you go for heavy doping, you're gonna compromise your lifetime, but you get conductive layer. On the other hand, if you move to low doping level, the layer is gonna be resistive, but you gain your lifetime. But it's gonna be electrically resistive, which also kills the device. So yeah, that's a trade-off that you have to understand when designing a device. Okay, especially if you're doing technology development, you can paham this concept properly, right? So being conductive is not always good for your device. So it's good only to some extent. So maksudnya when it comes to optimization, you really have to find a sweet spot kat mana be optimum point, right? All right. So recombination, when you talk about so we have discussed the abstract, the concept, the condition of recombination. Sekarang I would like to extend that into an actual sample. Katalah ni, I'm your remote aircon. This is your silicon layer, a silicon wafer, for example. It can be gallium arsenide, it can be some others, but just silicon as a reference. So the recombination that we have discussed will happen or may happen either in the bulk maksudnya dekat dalam volume ni if you're talking about 200 micron, then the bulk will be 200 micron, the whole thickness of the device, the whole volume of the device. It can also happen at the surface. Boleh jadi kat the very surface ni so ini dia boleh jadi kat the whole surface ni. Kalau your surface area is like, I don't know, 5 by 5 for example, and so that means the whole surface is prone to surface recombination. And the same goes to the back as well. It's another surface, isn't it? So that means your recombination may happen in the bulk. Kalau your bulk is like 10 micron, then your bulk is only 10 micron. Walaupun it's thin. So the bulk is referring to the volume that you have. And the other recombination is called surface recombination. So bulk recombination inside, surface recombination on the surfaces. Faham belakang, So both of these bulk and surface recombinations affect electronic quality of the material. So bila you nak fabricate transistors, LED, lasers, solid state drive, macam-macam lah, whatever device yang you can fabricate from a typical semiconductor material, electronic quality will be the prime parameter that you have to look at. Maksudnya before you do the fabrication, the incoming wafer from your supplier should be good, should be meeting minimum specifications. We call it specs atau specification in the industry, and they are a certain minimum lifetime. So for example, if you are a supply quality engineer which controls the incoming wafers before it goes through all the fabrication processes to be able to produce your transistors, for example, then you should be controlling the incoming material quality to meet at least, for example, 500 microsecond lifetime for every single wafer, at least. So if it's coming at 700 microsecond, is good. 500 microsecond is good. 300 microsecond, reject. So those are the things that you're gonna be dealing with when it comes to incoming wafer quality. Especially if you're working on in QA department and you are responsible for controlling the incoming material quality. Okay. So as far as this recombination concept is concerned, then we are talking about the lifetime of the incoming wafer or the electronic quality physically. Physically, kita panggil electronic quality lah. But what does it mean by that? Electronic quality is actually the lifetime and recombination. So this schematic shows the bar. Sama macam saya punya aircon ni, 5 aircon. So the width here is all the volume that you have. So typically, if you're talking about IC fabrication, like Silterra, Infinite, we're talking about this thickness in the range of 500 micron, 700 micron. If you're talking about a solar cell, for example, if you're talking about silicon based, then we're talking about 160 micron, 180 micron, and it's getting thinner and thinner in order to make it more cheaper over time. Okay. So it depends on the industry. So this W is dependent on the industry. And therefore it depends, the volume, the bulk recombination that you have is dependent on what you are working on specifically. On the other hand, if you're working on thin film devices, if you're working on silicon wafer, then we're talking about, say, 180 micron thickness, so twice of our hair thickness. If you're working on thin film devices, maybe your W here is in the range of 1 micron. 1 micron, yeah? And tadi 180 micron, 160 micron. So it's like 150 to 200 micron less in terms of its W, of its thickness. So when you compare, let me just test you in terms of the logic. Bila you are working on a thick device, 200 micron, let's say 200 micron lah, senang sikit. 200 micron, then you're going to have your bulk recombination, you're going to have your surface recombinations on top and at the back. In the other case, you're working on 2 micron thickness, W2 micron, and you are having the very same surface area at the front and the back. In which case, do you think your surface recombination will dominate? Is it in a thick device? Is it in a thin device? If you're talking about total recombination being the summation of surface recombination plus bulk recombination. You rasa surface recombination akan dominate the whole recombination in the device, in the thick device, or in the thin device? This would like to stretch your understanding a little bit. If you can explain that. Anyone? Or you don't know? Because if you reduce the W, your bulk recombination will reduce, isn't it? But the surface remains the same. So my question is, surface recombination will dominate the whole, over the whole recombination, in which case, whether it is in a thick device or in a thin device. Okay, interesting. Bala said thin, Fatul said thin. Right. Can you explain? Can you share your opinion? Why do you think is going to dominate in a thin device? Fatul or Bala, will you unmute yourself? I'd like to hear your opinion on this. Ni soalan application, so whatever that you learn here, I'm trying to stretch a little bit for you to do a bit of analysis based on the concept that we learn. It's not obvious, but then it will make sense eventually. So let's hear from you first.
Is it because total recombination is surface of bulk? So in a thin semiconductor, relatively the bulk recombination will be much lower than the surface recombination. So so in a thinner semiconductor, there'll be much higher surface recombination as compared to a bulk recombination, because just purely on the thickness factor.
Okay, all right, interesting. Thank you. Right, Fatul said lesser bulk recombination on thin device while surface still the same. All right, okay. If you are Fatul, if you are using that premise you mentioned in the chat box, we're expecting lesser bulk recombination in the thin device while the surface recombination remains the same. So holding on this premise, do you think surface recombination will dominate over the whole recombination in the thick or in the thin device? If you're holding that as your premise, not a question, yang lain tak tu, kayaknya betul lah tu, yang paling cakap tu betul. So then, as the result, surface is gonna dominate in the thick or in the thin. Thin ke, Fatul? Yes, thin device, right? So the answer is yes, correct. Okay, just like the way Bala explained, exactly, right? So kalau you imagine, if your bulk is dependent on the W, and as you go down, your surface remains the same, So maknanya I just slice this remote ataupun silicon lah, remote tak lah, I couldn't relate. Silicon, I slice say 1/10 or 1/20th out of the original thickness. Your bulk recombination reduces significantly already because of the effect of the W. It's been reduced. While the surfaces, top, bottom remains the same, isn't it? Maknanya you punya, kalau you assume that the dominance is mathematically is determined by surface recombination punya proportion over surface plus bulk as your total. Sebab total is given by surface plus bulk. So that means your numerator will be surface, your denominator will be surface plus bulk. Then your bulk is reduced already, but the portion of surface remains the same. So then the numerator will increase, isn't it? The proportion of the surface will increase significantly. So that means bila you can just exaggerate a bit like this. If you work on a very thin device, for example, if you're working on 500 nanometer, 100 nanometer, tapi surface area sama je. So practically your device ni is dominated by surface saja. Bulk ni macam almost negligible. You practically have surfaces to work on. But macam tak ada bulk lah, lebih kurang lah, exaggeration. So when Bala said relatively, that's very interesting because it's relative, isn't it? So it's relative. Dia ada bulk component, but then relatively bulk will become lesser and lesser, and therefore your surface will dominate. So if you're working in industry, eventually related to thin film devices, thin film transistor, thin film solar cell, thin film whatever, this surface recombination will become dominant in your devices instead of the bulk. But then the bulk component will be less important, I would say. I'm not saying that you can compromise a lifetime, but the contribution towards the whole recombination punya process will be lesser from the bulk. Okay, so that's the whole point. So good. So I'm trying to stretch the fundamental that we learned here to application so that you can relate, because when it comes to questions or nanti you nak buat technology development and so on, so you should be able to take this concept to your application and try to relate and try to make sense. Right, good. So recombination at the bulk, in the bulk and at the surface. Any defects or impurities, we're going to finish in like 5 to 10 minutes, and then kita akan stop for about 10 minutes, have a 10 minutes break for your coffee or toilet break or whatever. Then we're going to come back for another 40-50 minutes because we're going to have 2 hours for today. So defects, impurity within or at the surface. Within means in the bulk, dalam, okay, or at the surface here, the bonds. Promote recombination, okay, promote recombination. So you're going to have recombination in the bulk and at the surface at the same time. So since the surface of silicon wafer represents a severe disruption of the lattice, the surface of the solar cell or other devices represent sites for high recombination. So if you're working on silicon wafer, for example, so you're going to learn later on in 487 if you're taking fabrication, then you are going to learn that this piece of silicon wafer originates from a long ingot. Kita bincang awal tu, it's actually a long ingot that you have to slice. Right? You have to slice using a sawing process, diamond wire saw and so on and so forth, diamond blade. You can just slice to be able to produce wafers. When you slice, you're going to learn later on that when you grow an ingot, the ingot is typically a monocrystal. The single crystal, bila from the seed that you grow until the remaining ingot macam bantal kan, macam long bolster tu. So the whole thing is following the original crystalline orientation. So it's just a single crystal material. So when you cut the ingot into wafers, your surface ni is the result of the cutting process, isn't it? So you are technically terminating the lattice. Okay, macam you potong kayu kan. Bila you potong kayu kan, you tengok orang potong balap, kata kayu besar lah, for example, dia potong guna mesin tu. You're going to see all the habuk kan, all the dust flying around, isn't it? Kiri kanan. For example, if you imagine cutting kayu tu untuk buat meja kat taman rekreasi or whatever, a relatively thin slice for a table, for example, and you're going to see dust flying around. So those dust is the dust, the very same dust, silicon base that you should expect while doing the cutting. And doing the cutting is actually terminating the lattice. So that's what it means by this termination of lattice. Okay, disruption of lattice. Well, the moment you disrupt the lattice, you are inducing formation of defects. So that's why you have these dangling bonds. Dangling bond ni apa? Maksudnya your silicon bonds that are not bonded to the neighboring bonds. There's no, your silicon is truncated. It's supposed to be bonded to the next silicon, next silicon, next silicon, next silicon, but then you just cut, and the bonds at the surfaces at the back and the front surfaces, they are terminated. So this termination causes defect, and this defect causes surface recombination. So that's the whole point, right? So the high recombination rate in the vicinity of the surface depletes this region of minority carriers. So if you are generating minority carriers from your silicon material and you want to extract them, but then they recombine at the surface due to the dangling bonds, the presence of dangling bonds. So that means to be able to successfully extract your carriers from the bulk and eventually through the surface. So usually kita letak metal contact ke atas atau bawah to be able to extract the carriers or inject the carriers. On the other hand, they can recombine, right? So these are dangling bonds. So to be able to fix this and successfully extract the carriers, you need to make sure that the dangling bonds or the defects are gone or are removed. Okay. So therefore, the surface recombination rate is limited by the rate minority carriers move towards the surface. Yes. And the rate at which the minority carriers move to the surface, the speed, if you like, the velocity, is called surface recombination velocity. So in the units of centimeter per second, and it's used to specify recombination at the surface. So if you want to tell how good or how bad is your surface recombination, you have to look at this SRV, right? Surface recombination velocity. So high surface recombination velocity, high SRV, means the carriers from your bulk generated, generated in the bulk, will rush to the surface to recombine at higher velocity. And they laju rush to the surfaces to recombine. So that means high SRV is bad. High SRV translates into high recombination, high surface recombination. On the other hand, if you're talking about material with low SRV, you are talking about a lesser recombination at the surface and better material quality. Okay, high SRV is bad, low SRV is good. So that's why you have to get from the G's. In a surface with no recombination, the movement of carriers towards the surface is zero, hence the surface recombination velocity is zero. If you assume there's no surface recombination at all, then you should expect your SRV will be very, very low, which is zero. But it's never the case at all in the practical applications, right? It's never the case. Tapi kalau kita assume for the sake of calculation, yes, it can be done. But in the real case, there's no such thing, right? In a surface with infinitely fast recombination, high SRV, the movement of carriers toward the surface is limited by the maximum velocity they can attain. Typically for a typical semiconductor in the region of 10 to the 7 centimeter per second. So if you're comparing two materials, two silicon, for example, one silicon SRV 5,000 centimeter per second, second silicon SRV 10 centimeter per second, which one is a better silicon? 5,000 centimeter per second or 10 centimeter per second? The second one, right? So that means the 10 centimeter per second is a better silicon material, because low SRV means lower surface recombination, which is good for your device, right? So high SRV is bad, low SRV is good. So let me just finish with this. So how do you then fix this problem? So dangling bond ni bila you cut, when you cut the lattice, you cut the silicon, ataupun if you're working on any deposition process for your FYP, okay? If you're depositing by using sputtering, if you're depositing by using evaporation, if you're depositing by using CBD, if you're depositing by using sol gel, if you're depositing by spin coating, by CVD, chemical vapor deposition, or by some liquid-based processing, for example, for deposition, the same effect will be obtained as well. Bila you, on the other hand, macam tadi bila kita discuss, you cut silicon from an ingot, you're going to have defects, dangling bonds. Case number 1. Itu we call that as top down. Maknanya you ada something big, then you cut top down. On the other hand, if you grow bottom up, you build, right? You deposit on your glass, on your plastic, on your silicon, on your whatever. You are growing. Bila you grow, when you stop growing, you will end at surface, isn't it? You would deposit only like 50 nanometer, 100 nanometer, 1 micron, 10 micron, whatever. So you will also end up with the surface, and that surface is also a recombination center punya location. So it's not only limited to due to the cutting process from ingot, but it's also due to the growth process that will also result in formation of dangling bonds. So as long as you have termination of lattice, either by cutting or by growing, you are producing dangling bonds at the surface. So you can relate perhaps to your F1P if you're doing any growth, but you're doing some measurement, but you don't get anything perhaps. So that's probably due to recombination as well. Okay, surface recombination. So how to fix it? Macam mana nak solve this dangling bond? So to solve this dangling bond, we need to introduce a process that we call passivation. Okay, can have a look here, passivation. And this passivation, if you talk about this very same silicon, remember on the previous page we talked about bark and surface. Bark dekat dalam, surface dekat atas dan bawah. So when you talk about passivation, you can passivate the defects on the surface, the dangling bonds on the surface. That means you are the dangling bonds are dangling. Macam dia tak ada bond lah, tak ada bond. That's why we call it dangling. So how do you fix that? Is by passivating certain atoms to the dangling bonds. You are actually saturating the bond. Ataupun you close the bond lah, you tutup, you kunci dia lah, tak bagi dia dangle. So the moment you lock that or you saturate the bond, we call it technically, we call it saturating the bonds or passivating the bonds if you like, then you are doing surface passivation on the surface. At the same time, your bark, when you do your growth or whatever, you may have imperfect lattice as well. Okay, so below you the imperfect lattice, you may have some defects in the bark as well that you don't realize. So the defects are not just on the surfaces, but also in the bark. So that's why you also need a bark passivation. So when you talk about passivation, we are talking about both. Okay, not only one. We're talking about surface passivation and bark passivation, right? So that's what you should expect. So in this case, let's have a look at surface. The reduction of the number of dangling bonds and hence surface recombination is achieved by growing a layer on top of your semiconductor surface which ties up some of these dangling bonds. Ties up means saturating the bonds, ataupun you close the bond lah. There's no more dangling. So this reduction of dangling bond is known as surface passivation, right? So how does it help? So the lifetime of the material is contingent upon the consideration of minority carriers. When you passivate the bond, the minority will lower surface recombination or lower bark recombination. So the moment you passivate the defects, because dangling bonds are defects, so there's no more defects to be yang akan introduce or yang akan induce SRH recombination, isn't it? Because we talk about SRH is due to the defects. So the moment you saturate the defects, or you technically remove the defect from your forbidden gap, the trap states, remember? Then you're removing the trap states and then you are reducing the possibility of SRH recombination, which will then lead to improve carrier lifetime tau. And your lifetime tadi mungkin kalau banyak sangat defect, you are talking about 50 nanosecond perhaps. Tiba-tiba bila you passivate, after you've done the passivation process on the surface and at the bark, say it may improve to 100 microsecond. Originally 50 nanosecond, kejap ya, 10 to the 9 dah recombine, and after you do the passivation, then you can get the order to improve to microsecond. It can now survive up to microsecond. So that is the effect of passivation that you should expect, right? So it can lessen the rate at which a minority carrier is depleted. Depleted here means recombine. Remove. So if the rate of minority carrier depletion can be limited, the lifetime of the material can be improved. So since if the tau is improved, remember L is proportional to tau, L equals to square root of d tau. When your tau increases, your L increases. So that means the carriers can now travel through a longer distance and they can be extracted more successfully, right? So for silicon atom, if you're talking about silicon in the industry, typically we are using either hydrogen, usually hydrogen, in order to passivate the bark and the surface as well. Okay, so this hydrogen kalau you belajar dalam industry, then we typically use silicon nitride hydrogenated. So that means silicon nitride you are the hydrogen component. So you're gonna learn in 47 later on how to do the deposition of silicon nitride with hydrogen in. So the hydrogen incorporated within the silicon nitride deposited on the surface, when the silicon will go through a high temperature process, and the hydrogen will be driven into silicon lattice and passivate the bark and also passivate the surface successfully. And that will fix the lifetime issue. Okay. So these are all equations related to the device physics. I don't want to go through some of the recap of the previous concept that we learned. Mass action, NP, NI squared, all those stuff. Yeah, minority carriers, drift and diffusion, current density, the total current. Yeah. Right. So is everyone clear on the concept of combination, bulk and surface recombination, diffusion length, carrier lifetime, and eventually passivation for bulk and surface? Is it okay? Do you have any questions before we take a break for about 10 minutes? Ada soalan? No questions? All good? Right, so what's the time now? It's 10:56. So let's meet again around 11:06. Okay, so kita break for about 10 minutes. We'll see each other again at 11:06 and we'll continue with PN junction. Okay, so in PN junction, we're going to learn about the fundamental PN junction and then what happens at thermal equilibrium, what happens at the bias condition, and eventually under light illumination. Then we're going to be done by next week. Right, inshallah, we're going to be done by next week, and then you're going to go off for your mid-sem break. Before that, the test, and mid-sem break, and then when you start in the second half of semester, Dr. Marzani will continue to teach you on semiconductor devices. Okay, so let's have a 10 minutes break. I'll see you again 11:06. Bye, take care. Go down. Right, welcome back. So now let's continue with our next topic, which is on PN junction. Let me share the slides on PN junction. Right, could you please confirm if you can see the slide on the screen?
Yes, doctor.
Thank you. Right, so let's get started with PN junction. So as usual, before we continue, let's recap and let's challenge on what you've learned in the previous topic. So let's go through briefly. Question number 1. What is carrier diffusion length? What is carrier diffusion length? Anyone? Can unmute yourself, can write down in the chat box as well. We're going to use all this when we talk about PN junction and eventually your devices. Anyone, what is carrier diffusion length? Najia? Najia FYP student there. Najia, any idea? Diffusion length, carrier diffusion length. Anything? What is diffusion length? Ada Najia? Shalini? B Shalini?
The average length a carrier moves between generation and recombination.
Average what? One more time?
Average length a carrier moves between generation and recombination.
Right, very good. Average length, average distance traveled by the carrier between the point of generation and recombination. Very precise. Okay. Right, so let's move on to question number 2. How do we then calculate diffusion length? From the given definitions now, how do we calculate carrier diffusion length? What equation do we use? Zulaika? How do we calculate the diffusion length? L? Zulaika? Siapa yang saya tak pernah panggil ya? Alisa, Anis. Anis Amira. Anis ke? Amira? Tak pernah dengar suara ya? What equation do we use to calculate the L? Anis? Boleh unmute yourself. Anis Amira, Anis Shabira seorang ya, Anis Shabira. Your friend would like to assist Anis Shabira? Okay, right. Patul said here L. Yeah, right. L equals to square root of d tau, right? Product of d tau. We just learned a few minutes ago, right? L square root d tau. Right. Why recombination takes place at the surface of silicon or at the surface of any semiconductor material? Why do we have surface recombination? What induces surface recombination? Hang on. I'll recap a bit before we move on. Kuatin? Why do we have surface recombination? Kuatin ada? Selwan, Selwan? Tak nampak muka lah, susah sikit. Selwan, ya? Selwan Abdul Jabbar. Tak ada jawapan? Anyone? Why do we have surface recombination? You can write down. Right, defects, impurities at the surface. Okay, satu. Ada lagi? Any other potential reason why do we have? Yeah, dangling bonds. Right, so those are the reasons. Defects on the surface or dangling bonds. So those are the reasons why we have surface recombination. Do we want the SRV to be low or high? Why? So do you want your SRV to be high or low? Low, right? Good. We want it to be low. Why do we want it to be low? What does it mean when you say your SRV is low? Apa maksudnya? How does it make sense? So remember, you want to give meaning to the numbers. How does it make sense? Kenapa kita nak low? Yeah, low recombination. So the low velocity means the carriers are not rushing, if you like, rushing to the surface to recombine. So it's a measure of velocity where the carriers rush to the surface to recombine. Kalau dia laju, high SRV, that means dia laju sampai ke surface untuk recombine. Then if you can slow them down, if you like, slow them down, so dia akan slow dan sampai ke surface untuk recombine. So you're gonna have lesser probability of recombination with a low SRV. Okay. Right. Final question. How do we fix defective surface and bark in order to reduce surface recombination rate? What do we do? How do we fix the surface? How do we fix the bark? What do we do? Passivation. Good. Right? Passivation process. So let's just dive a bit more. For a silicon, what do we use to passivate the bark and passivate the surface? If you talk about the silicon, there are a range of many more materials. Cuma tadi dalam slide kita mention apa? What atoms do we use in order to passivate? Yes, you reduce the dangling bonds on top of the surface. Yes, but we use hydrogen generally, right? We can also use some other material. For example, you can use silicon dioxide to do passivation. Kalau you ada silicon and you have dangling bonds, you can just deposit a very thin layer of silicon dioxide, 10 nanometers, 20 nanometers, and the surface will be well passivated already, right? You can also use some other material like oxide-based aluminum oxide, Al2O3, to do passivation. Okay, so in our industry we have range of different materials that are used in order to perform passivation process. So among the common ones are hydrogen atoms. Okay, but you can use some other materials as well. Okay, so ada other option like that. Good. So those are the T's of the previous topic. So as I always said, if you are clear with this page, challenge what you've learned on the recap of the previous topic. If you're clear on this page, then you are clear more or less on the topic itself. Kalau you sangkut untuk tak faham nak jawab atau you don't understand what does it mean before you can answer, so that means you are still not cleared with your understanding on the previous topic. Okay, because these questions are the G's of the previous topic. So you better make sure that you are clear of every of this page. Okay, kalau you recap balik untuk test 1 nanti, if go back to every single page of this, before the new topic. Okay, and try to do revision at least based on this. Of course, you have to study more, but then if you can check on yourself based on these questions on the page, right? So that will tell you your understanding of the previous topic. Right, so now we are looking into PN junction. So it gets more interesting, it gets a bit more complicated, if you like, by the context, by the content, and by the calculation as well. So we're going to do some examples eventually in this topic. So you're going to look at a few things when you talk about PN junction. We are now combining a P and an N together as a junction, P and brought together. There are cases where you are bringing P and intrinsic in the middle and N, pin, S-P-I-N, or N-I-P if you reverse. Either way is fine, okay? So when you talk about PN junction, it doesn't have to be N on top of P all the time. It can also be P on top of N, depending on what do you want to achieve exactly, right? So you're going to see later on when it comes to the semiconductor devices, there'll be technologies that are based on N as the silicon, but you then diffuse P on top. There are some other cases where you use P as your silicon and diffuse N on top. It can also be that way, right? So we're going to look into introduction of PN junction. What is a PN junction at thermal equilibrium? How does it look like? How does it behave? PN junction with applied bias. So the moment you've got a thermal equilibrium, kita dah settle lah, if you like. Things happen already. You're going to see later on. And then you have reached thermal equilibrium condition, but then you want to disturb thermal equilibrium condition by applying bias. And you connect, you so sweep some voltage through the junction. Then you're going to see the effect of bias to your junction. And then what happens if you have already reached thermal equilibrium, but suddenly you shine light? Okay, macam you ada silicon, PN junction letak bawah matahari, then what exactly happens? And we learned a little bit of this when we talked about carrier injection last time, when we talked about light illumination, but that was just a brief or a very early part of this PN junction thing, and eventually application of PN junction. So PN junction forms the basis of many devices. So you talk about integrated circuit, the chips in your phones, in your laptop, in your gadgets, in your some other tabs, iPad, and other some other stuff. Consumer products in your TVs, in your whatever. Then LEDs, right? Then solar cells, then lasers, then bipolar junction transistors, then the chips in the cars for EV applications, for example, for some other typical conventional automotive applications. So they are all based on chips. And when you talk about chips and all these devices, they are all based on PN junctions. So the essence is PN junction. So therefore, the understanding of PN junction is very crucial. So when my colleagues ask about potential student to be channeled to the industry for their consideration and interviews and so on. So if you talk about the typical companies around Penang and Kulim, so the requirement that I normally get from the messages is we need students with semiconductor physics background. We need students with semiconductor background. We need students with fabrication background, all those stuff. Those are typical if you talk about semiconductor industries around Penang. So that's why this PN junction concept is very important. So what is then a PN junction? PN junction ni apa? So a PN junction is a boundary, is an interface between two semiconductor material of opposite polarity. So we're talking about bringing P-type material and N-type material together. So this P and N can be P-type crystalline silicon and P-type crystalline silicon, where we call this as homojunction. Homojunction means the material sama, band gap sama, homojunction. It can be P-type crystalline silicon and N-type amorphous silicon, and this is called heterojunction, because even though they are silicon in nature, but one is crystalline, one is amorphous. Crystalline is 1.12 eV and amorphous is 1.8 eV. So that makes heterojunction silicon. It can also be a p-type cadmium telluride, n-type cadmium sulfide. This is called heterojunction as well, but two different material. P-type cadmium telluride, n-type cadmium sulfide. So it can be n-type zinc oxide on p-type tin sulfide, SNS. So zinc oxide on SNS, it can also form a heterojunction. So when you talk about p-n junction in general, it can range from different combinations. It can be homo, it can be hetero, it can be really the same, it can be entirely different material system, if you like, right? So they are brought together to behave as a p-n junction. So one region of the material is doped with Na. Remember, we talked about Na and Nd. So that's why I reminded last time that the understanding of Na, P equals Na, N equals Nd, majority carriers, minority carriers is important. So one side is doped with p-type, another side is doped with n-type. Okay, one side majority carriers holes, another side majority carriers electrons. So the interface separating the p and n is referred to as metallurgical junction. So the central point there at the border, image kat bawah ni, I couldn't write with my stylus. There, this central line is called metallurgical junction, forming the interface together, right? So that is essentially a p-n junction. So what exactly happens when you bring a p-type material and an n-type materials together as a junction? What happens? So remember last time we talked about carrier transport phenomena. We have studied about drift. We have studied about diffusion, right? So when they are brought together, p and n-type, remember p-type material has holes as the majority carriers, and n-type material has electron as the majority carriers. So for now, let's just assume that we are combining p-type crystalline silicon with n-type crystalline silicon. Tak payah pening lagi fikir pasal cadmium sulfide, zinc oxide. Those heterojunctions, totally different concept. It's still a p-n junction, but then when we talk about the details within the band diagram and so on, it's going to be a bit different due to the different band gap, right? Due to different band gap and entirely different system, different material. But they are still p-n junction. For simplicity, for now, let's just assume crystalline silicon P and crystalline silicon N for understanding. So you're bringing holes beside electron as majority and majority. So apa yang akan jadi ialah you're gonna get holes from the p-type diffusing into n-type. Kenapa ada diffusion in this case? And electrons from the n side will be diffusing into p side. Why do you have diffusion in this case? Why do you get diffusion the moment you combine? Let's recap your previous topic. Anyone? Why do you have diffusion now? Exactly, that's the word. Concentration gradient. Okay. So remember, diffusion takes place because of the presence of concentration gradient. Now the gradient is simply because the hole is majority on the P, but minority on the N. Electron is the minority, majority in the N and minority in the P. So that makes the gradient, right? So the moment they see the gradient, they will diffuse across the boundaries and try to establish thermal equilibrium. Okay, so the moment you combine, dia bukan thermal equilibrium lagi, sebab dia ada movement. The moment you have that movement, it's not yet thermal equilibrium. We are going to establish thermal equilibrium condition eventually after the diffusion process stops. Sekarang kita baru nak combine, then it sees concentration gradient, they are going to cross over to P and to N until thermal equilibrium condition. So for simplicity, we are assuming that we are working on a uniformly doped junction. So that means you have a constant doping across your p-type, and you also have a constant doping across your n-type. So in some cases, when you work on the actual processor, there may be condition where you don't have exactly the same level of doping throughout the material, whether it's within P or within N. Kadang-kadang ada slight variation. So kita nak belajar the basic first. So that's why we assume uniformly doped across P, across N. And we are now assuming abrupt junction for simplicity. Apa maksud abrupt junction? So that means the junction here is square shape lah. The profile, if you look at this NA, or the Na this much, and the moment it gets into you move into N type, you're assuming it drops like that, a sharp drop in the profile, square shape, right? Square of the pulse like punya profile. And the same goes to ND. You start off high in the N and then you get nothing in the P. But it's not like you have nothing in the P because N electron is a minority carrier, isn't it? We learn about Ni, Np, Ni squared. Okay, whenever you have a majority, you're going to have your minority there as well at the molecular condition. Okay, kita assume for simplicity, simplicity. So once joined, excess electrons in the N will diffuse into P side. Excess holes in the P will diffuse into N side. Okay. So the movement of electrons to the P side, maksudnya movement of electrons from the N into the P, from the N into the P exposes positive ion charges. So remember, when you started off with N type, and then it's losing electron, isn't it? The atoms, the silicate atoms are losing valence electrons, traveling into the P side, and the moment the atom, each atom is lost with one electron, is going to be a positive charge. Dia akan create positive charge, guys, too. So you are going to expose this positive ion cores in the N side. And the same thing happens to P as well. We start off with P-type silicon with majority carriers holes. So the moment holes diffuse into N side, the original atom itu akan jadi negative ion cores, negative ion charges, if you like, same thing. And these positive ion charges in the N, opposite, you start off N, you akan dapat positive ion charge. You start off P, you're gonna get negative ion charges. And these ion charges only take place or only created near the junction, okay, near the junction. So that means you are going to have diffusion mainly from the region, let me use my cursor, from the region near the interface. And it's not happening across the P, it's not happening across the N, but you're going to have diffusion from the region near to the junction, because this is where this is the region where you see gradient. Kalau you are away from the junction, going further into P or further into N, you won't be able, or the carriers won't be able to see the concentration gradient, because kat depan dia ada banyak lagi same level of holes or same level of electrons. So it just doesn't see the gradient yet. So the place where they're going to see the gradient is close to the junction. So that will make the region close to the junction to be losing electrons in the N side and to be losing holes in the P side, exposing the ion cores near the junction. Okay. So we're going to see later on, don't worry. So the moment you're getting your positive charges in the N, negative charges in the P, so that will establish a built-in electric field. Okay, built-in electric field. And this region, this central region near to the junction in the P, into the N slightly, is called depletion region. Okay, this is the region where the majority carriers are depleted. So that's why kita panggil depletion region. Depleted due to, why is it depleted? Kenapa kita depleted of the carriers near the junction? Because of, why do we have depleted carriers, majority carrier near the junction? Sebab apa? Anyone?
Recombination.
Recombination, but before recombination, kenapa you are depleted of your carriers near the junction? Due to this diffusion, right? They diffuse. They left the region. So diffusion creates this positive and negative ion charges region, and this region is called depletion region. Okay, a built-in voltage results from this electric field formed at the junction. So the formation of ion charges will result in formation of electric field, and as a result, built-in voltage across the junction. Okay, so let's see. So let's go slightly into the material. So we have learned the concept of P equals to NA. So let's recap. And N equals to ND. So this is where I said last time, P naught and N naught. Okay. So the moment you see PP naught, what does it mean? What are the three things that you have to mention when you talking about PP naught? Anyone? Let's recall a bit. Remember the three things? What is PP naught? Anyone would like to unmute yourself? Or NN naught? Yep.
Holes in a p-type semiconductor thermal equilibrium.
Yeah, exactly. Good. So density of holes in p-type material at thermal equilibrium before they are brought together. Okay, and that equals to Na. So that equals to the doping level that you have originally in the p-type material. And the same goes for n-type. So the n-type doping level that you have can also be categorized as NN naught, the density of electrons in n-type material at thermal equilibrium, and that is approximately equal to ND, or NN naught equals to ND. You have to bear this in mind and be clear about this, because we're going to do calculation on the inverse as well. So these two, PP naught NA and N naught ND, are called majority carriers, which is due to the contribution of the doping. On the other hand, we have also discussed about minority carrier population, which is given by law of mass action. N times P equals to Ns squared. And in the p-type material, the minority carrier is labeled as NP naught. Okay, majority is labeled as PP naught. And the minority is therefore labeled as NP naught. That's why you have to understand the three things, the definition. So NP naught here is density of electrons, which is the minority carriers in p-type material, in the blue material on the left, at thermal equilibrium. And that's given by, you inverse the law of mass action, Ni squared over Na, and is given here as doping level. Then you can get your minority carriers readily available in the p-type material. And the same thing is applicable to in n-type material as well. And the minority carrier, the hole, is given by Pn naught. Density of holes in n-type material at thermal equilibrium, and that's given by N squared over Nd, right? So kalau you tengok kat sini, in the blue region, you have a lot of holes, the positive charges. The positive here, what we call denotes the holes. And you also have minority carrier kat sini, electron. So this NP is actually the NP naught, this PP is PP naught. On the right hand side, NN here is the majority, NN naught, and the minority here is PN naught. Naught is just a equilibrium condition. So the moment you combine, so gradient in carrier concentration at the junction, near the junction, it doesn't happen all the way throughout the P, all the way throughout the N, because they will not be able to see gradient if you go away from the junction. It will only happen near the junction region, okay? So the diffusion, that means the diffusion only happens near the junction. Ini dalam P tu yang diffuse yang dekat junction je, yang dekat interface. Dalam N pun yang diffusion dekat interface je. It's not throughout the region. Okay, so if you want to know, the region further away from the junction remains neutral. Maksudnya dia masih neutral as if it's not combined with any opposite junction, any opposite material. Okay, further away from the junction, it's subjective, of course. So the gradient in carrier concentration at the junction gives rise to diffusion of majority carriers due to concentration gradient. Holes flow from the p-type into n-type, and electrons flow from the n-type into p-type. And the movement of carriers from both sides give rise to diffusion current density. That's what we learned in the previous topic. And the diffusion current density here in this case, J diff due to hole, is given by negative QD dpdx, right? D is the diffusivity of holes, and the dpdx is concentration gradient across the region, okay? And the same goes for drift as well. The region near the junction becomes depleted of carriers due to the diffusion process, leaving behind fixed charges, okay? If you can imagine, this whole blue region on the left is the whole p-type, the whole region on the right is the whole n-type, but the region here, the light blue and light red near the junction area, is the region where the carriers are depleted. But here further away, you still have the carriers as original condition, but they're depleted. So when you have holes depleted from the light blue region, is going to expose negative ion charges, when the electrons are lost from this light red region, is going to expose positive ion charges. So this formation of negative and positive ion charges leads to formation of electric field and therefore built-in voltage, right? So the current that you're going to have associated with the movement of the carriers. So if you look at the holes, contribution of holes saja at this point, so the diffusion of holes is given by Q negative QD dPdx, and the drift of hole due to the presence of electric field across the junction is given by Q P mu H E. Okay, that's what we learned in the carrier transport phenomena, contribution from diffusion and drift. And the same thing goes to the electron as well. Okay, the same thing goes to electron as well. So in total, there are 4 currents that flow. So you're going to have 2 contributions from holes, diffusion and drift, and another 2 contributions from electrons, diffusion and drift. So 4 current flow in total. Eventually, the drift and diffusion currents balance, and the net current is 0. The net current is 0, though there is still movement of charge at microscopic level. So the net movement is assumed to be 0 due to the opposite and equal magnitude of the current flow, right? So the J drift electron is given by the very same equation. It's just that you change your concentration to N instead of P, and mu E instead of mu H, right? Or kalau you pakai N, then it's going to be P on the other side. And the diffusion current density for electron, diffusion current density for electron is given by QD and dx, right? So this is the same illustration at thermal equilibrium. So you can see here the gray area on the left is the region further away from the junction, the region on the right further away from the junction as well. And this central region is where you get the ion charges and where you are depleted of your carriers, and it's called depletion region or space charge region. Kalau you tengok ada text or references or question asking for what is the whatever in the depletion region or in the space charge region, so it's referring to the very same thing, same region, region yang ada ion charges positive and negative on both sides. And the electric field that you have is pointing to this direction on the left, and you're going to have a diffusion of holes and electrons beforehand, right? So if you dive a bit further, if you relate back to what we've done before, remember we've talked about Fermi level, we've talked about EC, EV, and all those stuff. Now we are going to use all of those concepts while discussing PN junction and see what actually happens when you combine P and N at the level of band diagram. Sebelum kita tengok just at carrier level, right? Carrier movement, right? Carrier movement, all this stuff. Now what happens to the Fermi level and the rest of the band diagram punya properties. So 2 isolated pieces of P and N at thermal equilibrium are at different Fermi levels. So let's recall. You have a P-type semiconductor, N-type semiconductor, P-type silicon, N-type silicon. Where's the Fermi level in this P-type? Where's the Fermi level in this P-type? Anyone? Let's recall our previous topic. Where's the position of EF in this P-type material? Can we give a reference point, perhaps?
Near the VB.
Near the VB, right? So it's given already on this page. Near the VB, or if you want to be more accurate, near EV, right? Electron valence band punya energy level. EV or VB is as a whole thing, right? So your EF in your P-type is close to EV. Your EF in your N-type is close to EC ataupun conduction band. And you know already that your majority carriers in P-type is given by PP0 equals to NA, and therefore your minority will be NP0 and the inverse of the law of mass action. And the same goes for N-type as well. Your NN0 is your ND, and therefore your NP0 is Ni squared over ND. And they are now independent. Now you're bringing them together, okay? This diagram is actually the band diagram before the combination of the junction. They are still independent of each other, just as the original condition. So the moment you bring them together, let's go on for another few minutes. So if you connect the two semiconductor pieces, two silicon together, P and N, the thermal equilibrium condition will be eventually established. Okay, eventually established. You're going to have a couple of things, a couple of processes inside before you eventually get thermal equilibrium condition. So what will happen when you bring these two Fermi level together? One is below, near the valence band, one is top, near the conduction band. You are going to have alignment of your EF. Right? Bila you join, okay, katalah saya letak, ni just relative, EF saya, this is P-type, my EF is below, near VB, this is my N-type, my EF is near the CB, ke atas. So what will happen, when you bring your P-N junction together, you are going to have diffusion started. Holes from P-type into N-type, electrons into N-type, from N-type into P-type. So the moment the concentration gradient is observed, you're going to have the diffusion. And the moment you are having diffusion process near the junction or in the junction or close to the junction, if you like, you are actually aligning this EF to a single level. This EF will come together as a single level. If you can imagine over time, if you have diffusion, they are now independent. You bring them together, diffusion start. Eventually, diffusion still start. You're gonna have drift slowly, and then you're gonna have diffusion. At one point where the diffusion stops, you are going to have a single Fermi level. And the moment you have achieved this single Fermi level, this is called thermal equilibrium condition. Okay? So if you look at this schematic diagram down here, you tengok kat bawah ni, the EF is originally below in the P side and originally on the top for the N side. But the moment you have brought them together, diffusion has taken place, and eventually diffusion stop, you are going to have a single EF within this PN junction material. Okay, so apa jadi? Bila you ada satu EF, that means your thermal equilibrium condition is achieved, and you're gonna get some band alignment kat sini. You're gonna get some band bending, bukan band alignment, band bending. Maknanya your EC, EV, P-type, your EC, EV, N-type, the bawah sikit. So you have to join them together by a bending in the junction region. Okay, so you should be able to draw this. Okay, I want you to practice drawing or sketching this ECEVEF before the PN junction and after PN junction formation, and draw the band bending. Okay, so the moment you've got your band bending, the moment you've got your single EF, that means thermal equilibrium condition, or TE, is already achieved, right? So when you join them together, the two Fermi level align because of a system at thermal equilibrium has only one FE or EF, sorry, EF, only one Fermi level. This alignment occurs very quickly by a carrier redistribution, by the diffusion process. When they're stable, there's no more gradient observed by the carriers. So well away from the junction, bulk condition dominates. So that means if you go away from the junction, condition ni macam sama aja. You are still with PP naught equals NA, NP naught equal NI over NA, and the same goes for N-type. Dia punya condition yang asal remain the same because they simply don't see the gradient because they're just away from the junction. Macam you kalau you pergi dekat, let's say if you imagine Grand Canyon, for example, in the US, you are away from the edge or from the cliff. You won't be able to see the drop ataupun the cliff just yet because you're just far away from the cliff. But as you are approaching the cliff, then you got to see a very high height and everything. You know, if you jump off the cliff, for example. So the very same thing here is applicable here, because if you're away from the junction, you won't be able to see the gradient, and therefore the condition persists as in the original condition, right? So upon the connection, the two pieces, you're gonna have redistribution of carriers. You're gonna get a redistribution of electrochemical potential, or EF. Then this bending and the single EF formation will result in a formation of energy barrier, Q psi naught. Okay, QVBI. This is also called QVBI. VBI is your built-in voltage, and your Q times VBI will give you the barrier that will stop further diffusion of carriers across the junction. So bila you form the barrier ni, is formed at thermal equilibrium. So the carriers from both sides, dia akan nampak ada tembok kat depan. Physically, just to make things easier. So dia akan nampak further a high barrier macam tembok that will stop them from diffusing to the neighboring region. And this will stop further diffusion process. Okay, maknanya dia kena block lah. Kalau a majority electron, dia akan stop, dia akan kena block in n side. Majority carriers hole, they can stop just in p side because of the barrier in between, and that's called energy barrier. Okay, so let me just this illustration is to explain the very same thing on what you're going to have upon combination of your p and n together. So you should be able to sketch this yourself. So energy on the y, x on the x, and then p side on the left with the Fermi level, EC/EV, n side on the right, EC level, and EC/EV. Kemudian ada band bending in the center, and then eventually formation of a single EF upon thermal equilibrium condition. And then before that, you should expect diffusion of electrons, red particle, from the n side into p side, and therefore drift will be the opposite direction. And the same thing happens to p side as well. Holes will be diffusing from the p side into n side, and drift is another way as well. So this is what's leading to the formation of the p-n junction. Okay, so is it okay so far? p-n junction, is it clear or is it confusing? So I'm going to continue on Monday on the rest of the stuff. We're going to do some calculation as well. I want you to try this out. And we're going to finish perhaps on Monday on this. I'm going to try some calculation as well in order to illustrate the point better, right? So is it okay? Do you understand the formation? How do you get a p-n junction? What's happening upon combination of p and n? The carrier transport mechanism when you have p and n combined together. Any question at all? Okay, clear? So if anyone is confused on the movement of carriers, diffusion and stuff, no, all good? Paham? Calculation based or theoretical? Good question. Test will be calculation based or theoretical. Okay, the test will be, well, it's not calculation per se, but it requires analysis as if you are doing calculation. Okay, macam calculation tapi will not be the calculation per se, tapi you have to do some analysis as if you do some calculation. So macam tadi kita tengok magnitude kan. So the magnitude thing is not calculation per se literally, but then you have to do some math in order to be able to see what happens next, something like that, right? So is the built-in voltage from the depletion region itself? Yes, good question. But then the depletion region give rise to the built-in voltage due to the formation of ion charges, fixed ion charges in this region. So these ion charges, negative and positive, are fixed. Dia macam, it's not moving, it's not moving. It's not like moving charges. It's fixed ion charges yang kehilangan electron or hole. So then, originally atoms, but due to the loss of electrons, they become positive charges, fixed. Due to the loss of holes, they become negative ion charges, fixed condition, fixed location. So this will give rise to electric field and therefore QVBI, the barrier. And the VBI there is actually the built-in voltage. So later on, so nak put things into perspective so that you can appreciate. We finished just now with this barrier formation, isn't it? This Q psi naught ataupun QVBI lah, if you like, QVBI, same thing, energy barrier. So this barrier is what stops the carriers from both sides, the majority carriers from further diffusing into the neighboring region, opposite region. So to be able to run operation in your PN junction devices, the carriers need to overcome the barrier. Eventually. Sekarang kita dekat thermal equilibrium, kita dapat single EF, then the barriers are there, they are stopped, they have stopped the diffusion. Maknanya dia macam lock in the original condition lah, due to the barrier. So to be able to run operation, the carriers need to overcome the barrier. Macam kalau apa you pergi training, apa physical training, you have to lompat tembok tu. Nak pergi ke belah sana, you have to lompat tembok tu. So how do you then overcome the barrier? Any idea for now? How do you then overcome the barrier? Kalau nak lepas tembok ke depan, what would you do? Or what would you need to do rather in order to make it easier for you to overcome the barrier? From human perspective lah, because that will be the thing that we're gonna, wow, yeah, trampoline, right? You need trampoline. You're gonna jump over it, yes, okay, good. Apa lagi yang you boleh buat agak-agak? If you have tools to do something on the barrier, what would you do? Climb, okay, you have to climb the barrier. Cut through, wow, this is interesting, right? Remove perhaps, or reduce the barrier, right? Kalau tinggi sangat, you can perhaps remove somehow the barrier. So this is the thing. These are the things that we're going to cover next, right? The moment you have understood the concept of thermal equilibrium. So what can we do next in order to manipulate, or manipulate is probably the word, or change, or modify the barrier that you have in the middle so that you can induce certain operations, right? So nanti kita akan tengok kenapa kita apply bias, PN junction under bias condition. What's going to happen to the barrier if you apply bias? You can go positive, you can go negative. What happens to the barrier next? And what happens if you shine light to the semiconductor? What happens to the barrier? What happens to the carriers? So these are the things. So the goal for today is just to establish a PN junction under thermal equilibrium. And you join, tinggal tak payah buat apa-apa, because you see here, no light, no voltage, no thermal differences. You don't induce anything. You just combine, let it be, and see what happens. So they will eventually form a thermal equilibrium condition where you achieve a single EF throughout your junction. Okay. Then we're going to do next, we're going to disturb the junction condition and see what happens to the barrier, to the carriers movement, and to the rest, to be able to induce operation of semiconductor devices. So this is why PN junction is the heart of the operation of your semiconductor devices, right? So any question? Any last question? Ada? Okay, that's how I want you to appreciate the thing, because so a good question just now by siapa tadi tanya soalan? Was it Fatin? Fatin tanya kan? So that question actually unleash few more things that you're going to learn later on. Okay, apa the region ada apa ni? Built-in voltage is from the region, and therefore next we are going to need to manipulate this in order to do something for our devices, right? So let's continue on Monday, and hopefully we should be able to finish everything next week for my topics, and then you're gonna go for a mid-sem break and come back for the devices with Dr. Mazani. Right? If there's no question, I'll see you next time. Bye bye. Take care. Assalamualaikum.
Thank you, Doctor.
No worries.